Good day to everyone. Today we're going to discuss the second method under open methods, which is the secant method. So for secant method, this is an alternative approach when we do not or cannot find the derivative of a function. Okay? So unlike for Newton-Raphson, which will require us to solve for the derivative, so if we could not apply the Newton-Raphson method in the equation, then we could apply the secant method. So in Newton-Raphson, the slope is substituted now with a backward finite divided by the difference. Okay? So with that, the derivative supposedly can now be computed as f of xi minus 1 minus fxi divided by xi minus 1 minus x sub I. Okay? So this one is a graphical illustration of your second method. So we have here your second line. So instead of the tangent, we'll be using your second line. Diba sa Newton-Raphson, we use the slope. So in here, we'll be using the secant. So the equation now will be based from here. So we have your initial guess. And then this one is your x1 or xi minus I. And this will be your true value. Okay. So from here, applying the equation of Newton-Raphson, which is xi minus f x sub I divided by f prime xi. So, sa substitute lang natin yung derivative. Instead na derivative ang gagamitin, we'll now be using this equation for the second formula. So, we still have xi. So, we'll have fxi divided by f prime xi. So, sinimplify lang natin siya. Okay? So, it's still the same, almost the same as for Newton-Raphson. Nagkaroon lang ng difference with the, with the equation for f prime of x sub I. Okay, so this one will be your working equation in solving for the value of x for each iterations. So for a continuous function, f of x equal to 0, we have the following procedure or algorithm. So step 1 is we choose an initial value, x minus 1 and x0 or x sub 0. And then step 2, we compute your estimate or the iteration of x or approximate value of x by using the second formula. And then step 3, compute for your relative error, approximate relative error, E sub E. So same equation for E sub E, mu minus all divided by mu value of x times 100. Then for step 4, same condition. If your approximate error is less than the stopping criterion, then we terminate. Else, we repeat step 2 and step 3. So for secant method, there are several advantages. This would include that it would converge faster than the bisection method. It would not require a derivative. So if you are having a hard time in finding derivatives of equations, then the secant method is for you. But if you are good at finding derivatives, then you can use the Newton-Raphson method. So another advantage is that it will only require one function evaluation per iteration. So ang hinahanap lang dito will be f of x sub I. Unlike for the Newton-Raphson wherein you will be checking the function of x sub I and the function of the derivative of x sub I. Okay? The disadvantages, so if there's advantage, there are also disadvantages. For secant method, there's a probability that our values or our iterations will not converge throughout our process. So there's no guaranteed error bound for computed iterations. And like it would likely be difficult if f prime or the f prime wherein x is equal to a is 0, that would now have the graph of our y, which is the function of x, at wherein x is equal to a, will be tangent to the x-axis. So meaning, hindi parang iisa lang if ever yung magiging value ng root natin, which will be very difficult to find a initial value of x sub or x sub o or negative x1 minus I. Okay? So for second method also, Newton's method would be generalized more easily compared to second method for new methods in solving simultaneous systems of nonlinear equations. Anyways, all of the methods that we have discussed would have advantages and disadvantages depending on the given equations. Okay? So to understand second method, let's have some example. So we have here a given function f of x is equal to negative 12 minus 21x plus 18 x squared minus 2.4x cubed. So though this is can be differentiated and can be applied with Newton-Raphson method, let's apply second method with this equation using initial guesses. X minus 1 is equal to, or x of negative 1 is equal to 1 and x sub 0 is equal to 1.3. Let's set our stopping criterion at 3%. Okay, so for our solution, first iteration, we're given x of negative 1 is equal to 1 and x0 is 1.3. So we solve for their functions, negative 17.4 and negative 14.528. So with that, we can now compute for our estimation or our approximation iteration of x. So we have x sub I now will be equivalent to 1.3. So minus f of 1.3 is 14.528 negative. So multiply to 1 minus 1.3 divided by 17.4 negative minus, so it becomes positive 14.1520. So tandaan lang natin yung bagong value, yung latest, minus the function of the latest times the old minus the new divided by the function of the old minus the new. Okay, so x new, f new, x old minus x new divided by f old minus f new. Okay, so that would be your reminder for the equation for second method. So simplifying now our equation, we get x1 is equal to 2.6075. So we solve for your approximate error. Old minus or new minus old divided by new. We get now a value of 50.14%, which is greater than our stopping criterion. So meaning we have to continue with our iteration. So for our second iteration, so x sub o now is 1.3. X sub 1 is 2.6075. Or this is old, this is new. So the function of the old is negative 14.528. The new one is 13.0770. So apply our values in our given equation. So that will now be the current or the new 2.6075 minus 13.07 times 1.3 minus 2.6075 all over negative 14.1528 minus 13.0770, which will give us a value of x sub 2 equal to 1.9796. So computing for our approximate error, that will now be new minus all divided by new, which will give us 31.72%, which is still greater than our stopping criterion. So we have to continue again with the next iteration. So for the third iteration, so we'll have to use 2.6075. X sub 2 is 1.9796. Their functions are as follows. So 130770. For x2, it's negative 1.6514. Substitute in our equation for our approximate root or approximate x, which will give us x sub 3 equal to 2.0500. And solving for the approximate error, relative error, that will now give us a value of 3.43%, which is greater than 3% pa rin. So we have to continue with our iteration. So for the fourth iteration, x sub 2 now is 1.9796. X sub 3 is 2.0500. You were able to compute already a while ago the function of x sub 2. Compute for the function of x sub 3, and it will give us negative 0.0813. Substitute this in our equation for the approximate x. So we'll have 2.05 minus negative 0.0813 times 1.9796 minus 2.05 divided by negative 1.6514 minus negative 0.0813. So we'll have x sub 4 equal to 2.0536. So computing now for the approximate relative error, we have 0.18. So it's less than our stopping criterion, so we can stop now with our iteration. So we terminate our solution. So therefore, the root now of the equation, negative 12 minus 21x plus 18x squared minus 2.7x cubed is 0, one of its root is 2.0536. Okay? So for our second method, we could again present or summarize our solutions in tabular form. So we have the iteration I, xi minus 1, xi, the functions of the values of the x's here. Then we have our estimated root and your approximate error in percent. So for 1, we have computed already our values. Okay, so this was our initial computation. So for the second iteration, your x1 minus I will simply be xi. So ito, lagay ko dito. It's 1.3. Yung xi ko will be the value computed here at x1 plus I. So that's 2.6075. Just substitute the values of xi minus 1 and xi in the equation. So we have your functions. And then compute now for x1 plus I using our second formula. And then compute for your EA. So same procedure for the third and the fourth iterations. Okay? So ma-observe nyo, yung xi, nalilipat lang siya doon sa xi minus 1. So kung may fifth iteration tayo, itong 2.05, bababa siya dito. Tapos lahat ng values natin sa x1 plus I, nalilipat doon sa xi. So kung may fifth iteration, yung x sub I natin, for the fifth iteration will now be 2.0536. So bababa yan dito. And then you can follow the procedure. Okay? So that's it for the second method for open method under open methods for finding or determining the roots of nonlinear equation. So thank you for listening.